Okay, so without any further delay, maybe Alex will tell uh, after the talk what he was wanted to say in advance. But anyway, it's really a great pleasure to have Milgrom here in Budapest. And yeah, I was lucky to meet him during the fall semester in Berkeley. He had this nice program at Berkeley. It was about matching an option. So Paul was essentially there for the full time, and the week came for the 3 days at least. And so it was really great to hear not just him, but also other younger researchers speaking about options. So I personally I learned a lot. So I hope that you will now also hear some very interesting, I guess, practical and results about options. So without any further ado, let's give Paul the floor.
Thank you. Is this working? Can you guys hear me okay? Yes. Great, great. Well, thank you for the introduction. I remember us going to a Stanford football game together too while you were visiting at Berkeley. And it's a great honor to be here. I mean, I'm mostly here to honor Vince, who is certainly one of the great scholars of my generation, and it's just a real pleasure to be here to help honor you, Vince, along with all of the rest of you. What I want to talk to you today, I mean, in my own career, at least the latter parts of my career, theory and practice have come together a lot, and I want to talk to you a little bit about a new part of theory that has been of some interest to me, a part that's been less formalized in many ways, and it has to do with transforming rights and mechanisms for doing that. I've already been involved in doing that in radio spectrum. I'm hoping to get involved in doing that in water in the U.S. West, and that's why the title appears as it does there. I'm going to step forward a little bit so I can see what I was talking about as I talk to you. And I guess I wanted to start off by talking about some old traditional theory that was mostly in words. Back in the 1920s, 100 years ago, Pigou proposed that we should tax and subsidize externality causing activities. So we would have the negative externalities, we would have taxes, positive externalities, we would have subsidies, and that would help restore first order conditions and improve efficiency. And famously, and the Chicago view, and for many years, almost the dominant view in economics, is Coase, who disagreed and said that the problem actually was the lack of secure and tradable rights. I put up here a factories emitting smoke because one of Coase's famous examples, he talked about a factory and a laundry, and they're near each other in the town. The factories are emitting smoke, and it's spoiling the laundry, which is hanging clothes on the outside. It's a real old example, but still it's one that appears in Coase. And Coase says, the problem isn't the externality. The problem is it's not clear whether it's better to emit smoke or whether it's better to abate the smoke so that the laundry can operate. But if there were clear tradable rights, they could negotiate over it, however the rights were allocated initially. If they were allocated to the factory, they could be bought back by the laundry. If they were allocated to the laundry, they could be bought by the factory. And if only we had clear tradable rights, Coase argued, we wouldn't have to worry about taxing and subsidizing externalities, having the government try to figure out how much it's worth. That individual negotiations, people would decide what it was worth. So he argued private trade would best promote efficient outcomes. This is a very influential argument, and I think it's wrong. Is why I'm beginning with it. His analysis has been disputed. I've been influenced in particular. His paper, well, Tori Ellingson has a new book actually, has this and many other things in it. but his paper confining the Coase theorem, contracting, ownership and free riding. What goes on in this paper is, all of Coase's examples, this is what Torres says in his book, all of Coase's examples are always about two parties. And when you have two parties, it's, they get together, they make an agreement, okay, maybe it works okay for two parties, this is confining the Coase theorem. But what if there are multiple parties? What if the smoke is affecting not just the laundry, but other businesses and other people around? And you try to get together a group of people who's going to negotiate to bring about the abatement. And now you have a problem when you're trying to bring about the abatement that that Vince decides it's very clever not to participate in this group and let everybody else pay for abating the externality. They'll still enjoy the reduced smoke. Well, so this is supposed to be a model, unlike some of our incomplete information models, where we get necessary inefficiencies. This is perfect information. Everybody is there's no asymmetric information. Suppose we know what everything is worth to everyone, but we need a negotiation. Somebody has to agree to pay. Well, there's a free rider problem. Some people can decide they're not going to participate. And as soon as you get a free rider problem, you can start to see why it can become difficult. The externality might not be effectively abated. And there's been some interesting work. I've been talking about this for a few years, and some of my students have started to do interesting work with former students. Here's one that I'm going to talk a little bit more about today. Not my students, but Billy Ferguson, who was one of my students actually. We've written a bit about market design for surface water. I'll talk to you a bit about that. There's lots of externalities involved in surface water, and I will explain what some of them are and how they're hard to abate. Peter Dvorak and Ellen Muir, both former students of mine, have a new paper, a recent paper called "The Mechanism Design Approach to Property Rights." And this is something that has come up in my consulting career, where people have asked me, for example, with the radio spectrum, where I've done a lot of work, people ask, well, how long should a license run? How long should the license be for? 10 years, 20 years? We figure, the spectrum use is not permanent. At some point, we might want to repurpose the spectrum. But, if it's 10 years, what happens if we need investments in year 8? Maybe the people who have a license that's going to expire in 2 years won't be willing to invest near the end of its life. We might have to trade off investment versus flexibility, and that kind of trade-off is built in a particular mechanism design model by these guys. Bing is here somewhere too. Bing, where she is, but Big Lou and Billy also have a paper defining rights to the commons, where the question is about who has veto rights. You have somebody who lives on your street and they want to paint their house pink, and it affects everybody in the neighborhood. Or they want to build an addition, or various things that people might want to do. Who should have the right to say no? And how do we coordinate the rights when there are multiple people potentially affected? So these are all situations in which Coase's analysis doesn't apply. And they're a classic, by the way, all of you who've done mechanism done mechanism design with incomplete information, where it gets hard when there are many people who have a modest contribution to value to their free rider problems become even more severe in models with incomplete information. So what happens in reality, sometimes is property rights do get changed. Radio spectrum does get moved. I was involved, and I'll tell you more about it later, movement of television from of spectrum out of use in broadcast television and into use in mobile broadband. The technologies have been changing and the values changed enormously. And we'll talk some about that. But classically, urban redevelopment. We have urban renewal and redevelopment. We have in the United States eminent domain. I'm sure there must be some comparable possibilities in Europe. where this is written right into the US Constitution. The founders in the US were aware that they wanted to protect property, but they also wanted to allow governments to do things that were productive. And they put in guardrails. There had to be a public use reason to seize private property, and there had to be just compensation, which has come to mean essentially fair market value to take property from the individual. I'm going to tell you a little later about the U.S. broadcast incentive auction, as an example on which I intend to build or try to build. It's a mostly voluntary process that where we reorganized the U.S. television industry for over-the-air broadcast, shifting use of a large fraction of the spectrum from over-the-air TV broadcast to wireless broadband. In the when we started doing this in the early 2000s, when after Obama was elected in 2008, right? There was a desired recognition that people were more and more watching television, satellite, cable, and eventually over the internet, and fewer were watching live television over the air. So the value of spectrum over the air was falling. The demand for mobile broadband for wireless communications was rising, and there are reasons which I'll talk about a little bit more later why bilateral trade was not a good solution to that problem. You couldn't just have, AT&T or Verizon go and buy a television station in Chicago and use that spectrum for technological reasons that I'll try to give you a hint about later. It really was a collective action problem to get all the TV broadcasters and all the phone companies to coordinate, shift the TV broadcasters into blocks of spectrum that are compatible with each other, clear some of the spectrum for mobile broadband, sell that spectrum to raise the money to pay the TV broadcasters and figure out how much spectrum to transfer. It was really a complex problem that I'll tell you more about later. But what's gotten me interested in this again is water rights in California and the US West. And we're still working on developing a water incentive auction along the lines that borrows some ideas from the broadcast incentive auction. And I'll tell you about that as well. So let me start by talking about a little bit about water markets and why they're complicated and why this isn't just a trivial problem. And this is a map from a little east of Sacramento, California, about a hydrological network. And let's see if I can get enough of a dot from this to see anything. Well, let's take a look at this little, the blue lines here, by the way, are streams, and the yellow lines, these yellow lines are canals, and these little red dots, the green dot indicate rights holders, that this guy has the right to use some water that comes from the stream. It's diverted at this point up here. The green lines are diversions where there is a pipe or something that will divert water from the stream to farmers at these locations. And then the red lines indicate return flow. So this farmer over here, if he takes water from over there, he puts 100 acre feet of water down onto his field, and some fraction of it, let's say 50 acre feet of it, either evaporates or goes into the crop. It's called transpiration. If it goes into the crop, into the air in that way. And so evapotranspiration is the water that's actually used, and the other water goes down into the ground, and some of it recharges aquifers, and some of it flows back into a stream. This guy's water flows back into that stream and into that stream. So it flows into two other streams, where the very same molecules can be used again by another farmer. And water is not like oil. It's not something that when you burn it up, you've used it and nobody else can use it. Water, there's a water cycle. Water, once you've used it, somehow or other can get used by others. And in this case, I'm emphasizing the return flow complexity. Okay, so users can return water to the original stream of diversion, but also to others. So that creates problems. This is one of Billy's examples. So here's two parallel streams. Let's see if I can see the back here. I don't even see it anymore. There it is. 40 acre feet of water is flowing down this stream, and 48 in some seasons, and 40 acre feet of water is flowing down the other stream. And Bob and Alice on the left-hand stream have diversion rights of 20 and 25 acre feet, which you might think were incompatible. And Charlie has diversion rights of 45 acre feet, which we'll see harder, right? Because it's 40 acre feet flowing down there. But the red arrows indicate return flows. When Bob takes his 20 acre feet out, 5 acre feet returns to each of those streams. And the result is that Charlie can get his 45 acre feet and Alice can get her 25 acre feet. Okay, so this is something that can happen in an hydrological network. Now, suppose that Alice has, so by the way, the farmers are not all the same, not by a long shot. Some of them have tree crops that just absolutely need to be irrigated every year. Others have fields, maybe they're growing alfalfa, they can let the field lie fallow in a low water year. So the marginal value of water can vary a lot from year to year among users. So let's suppose we're in a year when it turns out that Alice has more marginal value for water than Bob does. He wants to buy 8 acre feet from Bob. So 8 acre feet is to be bought from Bob. He's got diversion rights to 20 acre feet. So he diverts only 12 acre feet, and that's the other 8 acre feet continue to flow. But now, since he's taking only 12 acre feet, his return flows to the two streams still 50% in this example, so he's returning only 3 acre feet to each of these streams. So Alice now is able to divert 31 acre feet, and Charlie is able now to divert only 43 acre feet, so we have a range of 45. And in California, that Charlie can say, you can't make that trade. That's illegal. This trade harms me. And there's an externality. The trade harms me, and I won't let you make it. Now you might think if you were co-seeing that Charlie could, just make a deal with Bob and Alice, starts to get complicated. It's a three-way deal, but let's suppose that Charlie tries to make a deal with Bob and Alice. Well, the problem is, nobody knew how much the return flows were. All Charlie knows is he's not getting as much water as he should. He doesn't know exactly what's going on, and he knows that whatever's happening over here is not good for him. And he's against any change. This makes it even harder to make a deal that would be simple multi-valuable arguments. Okay. So this is something. So here's part of what's happened. And by the way, the idea here that Bob was using only half of the water that he took, that is also not clear. It was the water on the field. How much of it evaporates? How much of it goes up into his crop? How much of it goes down into the aquifer? Nobody had a clue what those numbers were. Makes it hard to arrange change or trade. Now it's getting easier. This is a photo that I took on the web from a website called OpenET. ET is evapotranspiration. This photo shows an area, a similar area in California. And what you're seeing is water use, I can't see very well, but you're seeing water use on a particular field that is measured by satellites. And it knows how much water is evaporating or transpiring. That is, it can tell how much water is going into the air from satellite detectors, which is a tremendous improvement in measurement. And if you can measure something, you can start to base rights on it, right? You can change the rights from the diversion rights to, in principle, that you change the rights, or you can set up the rights as being use rights rather than diversion rights. And those things that's useful because they come more nearer to adding up. That is it's the total water being used rather than the total water being diverted that is approximately constrained by the system. And here you see, it's showing you field by field how big the field is, and how much water is used month by month and how much water is used in total. And we can measure that on a daily basis, what the water use is out of each field. So that opens new opportunities for defining rights and for trying to set up a workable kind of system. Okay, and by the way, once you have rights that are based on use that more nearly add up, if they exactly add up, then we're fine. We don't have to worry about externalities anymore. If the amount that Alex used plus the amount that I use is allowed to be anything up to a total of 50, then we can do a trade and it in principle doesn't affect anyone else. In reality, it does, but we can start to ask about what to do about that. We can start to create markets where this holds at least approximately, and where we can tell at least approximately how much you're losing if I may, how much the rest of you is losing if we make a trade. Okay, so how do we get from here to there? Suppose we figure out how we want the rights to be. We want to create rights, and by the way, this is in my paper with Billy. It's very anti-Coasean because Coase talks about setting up rights in order to eliminate externalities, and we're talking about there being a trade-off between rights and externalities. If the depending on who's affected, you can protect more people who were affected by giving them each veto rights. But that raises transactions costs in Coasean language. It makes trading harder. So you'd like to have fewer of those rights. If you want fewer of those rights, you'd like rights of those veto rights. You'd like the permissions that people have to be largely externality free. So you want to reduce externalities in order to reduce transactions costs, rather than some other relationship that Coase had in mind. Anyway, the one question you might ask yourself is there a process getting from here to there? And the process is hard. I don't mean to make oversimplify, but I'll tell you that something was done in radio spectrum and may provide a model for doing something in water. One of the problems we have in water is that the water itself doesn't actually belong to the farmers. They have water in California, in the California Constitution, there's a human right to water. I don't know what that means exactly. There's a human right to water. It's not considered a private good that can be bought and sold. And I talk to lawyers about this. They don't know what it means either. But it's in the California Constitution. There's also a right for any Californians. There's also a right to go fishing. There's a human right in California, which has been determined to mean that the state of California has to ensure that there's at least one place where you can go fishing somewhere in the state. So that one they worked out, but human right to the waters they haven't. Anyway, so one of the problems is that a lot of the water is controlled by irrigation districts. And if we're going to have trade, it's going to be important to move that from the rights from the irrigation districts to the users. We have to redefine rights to make that feasible. Then we need a public database that and an official hydrologic model. We need to figure out who's affected so that we can assess where the externalities may lay and how we can mitigate them. And we need an official model of that to do that. And we need a database so people even know what people's rights are. It turns out a lot of these rights were established historically a long time ago and were never really recorded anywhere. And people just claim, well, this is what I've traditionally been using. So we need a database, which by the way is I've heard talked about in market design a lot. I think databases are really critical. I know Al was somewhere over there. Very well, but when you set up the New England Kidney Exchange, I mean, the first thing to do is to figure out, who needs a kidney and what kidneys are available and what their characteristics are. You can't have any trade till you've set up your database. Well, that's true about lots of things in market design. Have a recognized measure of what's consumptive use. I'll show you such a thing. offer a conversion, to a voluntary conversion. These are property rights, so in California, we can't seize these rights. But we can create a voluntary process to create secure, storable, tradable, consumptive rights, but only in places where the externalities aren't too large. One of the problems we have to work, one of the other things that makes this complicated is that if you have a right to surface water and you trade it away, you may say, well, I'm just gonna irrigate my fields by pumping groundwater, but groundwater is also overdrawn in California, and you're just trading one problem for another. So we have to carefully integrate these things. See if you're sure about that. Then conduct an incentive auction to incentivize additional conversion. So this is one of the key things that makes the work that I've done different from the work that others have done. This process that we think needs to go on can be done in a way that's voluntary. We have lots and lots of people who have property rights, and they can veto anything that takes away their rights. But we don't actually need to convert all of the rights to this new form in order to establish trading. We need a process that successfully converts enough of the rights. We need, you know, if trying to move some water from, let's say, rural uses, which consume about 80% of the water in California, to urban users, which maybe needs another 3 or 4% to have plenty. You know, if you were to get half of the rural uses to be converted to the new form of rights, you'd have plenty of potential supply for an active auction. You don't need everybody, and consequently, you bring about this change in a voluntary way if you can get the ownership rights down to the level of the farmers. And then finally, there's beneficial use provisions. This has to do in California, you're not allowed to waste water. So if you have a historical use of water that's wasteful, the state can take that water back from you. But wasteful is something people litigate. The California Supreme Court has said that the definition of beneficial use can change over time. And I anticipate that the definition economists would like of beneficial use is related to price. We would find out that the price of water is $200 an acre foot. If you have a use that's less than $50 an acre foot in value, you'd say that's not a beneficial use. We put ourselves in the circumstance where we'd be able to take away some of the least efficient uses unless those rights were then sold. Okay. So with that in mind, this may sound like a lot, and by the way, it is a lot. I have no promises of success in pulling this off, but we have pulled off one big one, and I want to go back to what was involved in it and what we did, and also I'm proud of some of the details that I thought I'd get a chance to tell you about some today. So, and you know, oh, and by the way, latest thing. So it turns out this is my evidence that this was really well regarded. The television industry is giving my company an Emmy Award this year in 2024. I think I'm going to be the first economist to win an Emmy. It's a technical Emmy for like I invented in new cameras. It's a method that we use to reorganize the television industry. It will be recognized this year with an Emmy. Okay, so for those of you who don't know what the broadcast incentive auction was about, here's a little video for you to back.
Electromagnetic spectrum, or just spectrum, is the huge range of wireless frequencies used for all sorts of different things, from X-rays to microwaves, garage door openers and baby monitors to broadcast television. Everything wireless uses spectrum. There's a certain part of spectrum that is particularly useful for various technologies. This spectrum is licensed by the government to different users so that the signals don't interfere with each other. Companies that run satellites, radio, mobile phones, and broadcast television all license different parts of spectrum. But what we really want to focus on is spectrum that's part of the Broadcast Spectrum Incentive Auction. The process for this auction begins in late 2015 and will involve the FCC buying some of the licensed spectrum from broadcast television and then selling it to wireless broadband companies. 5 years ago, the Federal Communications Commission, the FCC, proposed the idea for an auction in the National Broadband Plan. Congress authorized the FCC to proceed a couple of years later. And for the last few years, the FCC has been sketching out the detailed and involved roles for this first ever incentive auction. There are 3 interrelated components to this process. There's a reverse auction, where broadcasters will voluntarily decide whether or not to sell their spectrum rights to the FCC. Broadcasters will bid downward against each other to give up their spectrum. At the same time, wireless broadband providers will bid upward in a forward auction to buy that spectrum. Finally, there's repacking, a mandatory nationwide process where all broadcasters that stay on the air may be required to move to new channels. The FCC will begin the auction process later this year, with station applications to participate due in November or December. The actual auction will start on March 29, 2016, and will take somewhere between a few weeks and a few months. After the auction is completed, likely in the late spring or early summer of 2016, the FCC will announce the results and everyone's new channel assignments. Why is this happening? It's to really address wireless industry demand for spectrum, to increase broadband availability in the country, and to generate revenue for a number of government initiatives. Because the difference between what is paid in a forward auction and what is paid out in the reverse will be kept by the government for these purposes. Who will it affect? In terms of the voluntary auction, nearly every station will get an opening offer to sell. But ultimately, the FCC is expected to buy spectrum in large markets, geographically adjacent markets, or congested markets where there are a lot of broadcasters. As for the repacking, that will be a mandatory nationwide process that could affect any station on any channel in any market.
Okay, so that was the process, and I promised to tell you a little bit about the externalities. You need to have the, for a well-designed allocation of the spectrum, you need to have a bunch of channels where all the broadcasters are present. So it's not enough to buy channel 37 in Chicago and channel 42 in Detroit and so on, and try to, you can't build a broadband network that way. There needs to be, it's a problem that required coordination among the different TV stations. And then the TV stations that didn't sell, some of them have to change to start broadcasting on a new channel in order to allow the channel to be completely clear. The things called guard bands that in between broadcast television and mobile broadband, there needs to be some spectrum that's not put to either of those uses because the signals leak, too much into the technology of that. And somebody has to pay for that, of course, and a single buyer doesn't want to pay for government. So there was a lot of reasons why this was a collective action problem and needed to be coordinated on a large scale. Now, the way this thing went, and again, you'll notice some similarities to the ideas that I'm going to propose for water. It began with a study. So I've told you we need a hydrological model. Well, we needed a spectrum interference model to decide where we could put things without increasing the amount of interference that a station was getting. So there was a study done by the Federal Communications Commission. It took a look at it pixelated the United States into 1 kilometer squares, about roughly 10 million pixels, and it figured out from each TV station on each channel what the signal strength would be at the center point of each pixel, which is used to represent the signal strength in that pixel. And then it asks where is there going to be interference if between your two stations. These two stations interfere over here, and it's a Venn diagram. So some places, if you just count it, you'd be overcounting. This was created, and in order to, and the basic idea was that legal constraint. This is a funny one, and the law has these funny implications for market design. Interference is measured in whole numbers of percentages. And anything less than 0.5% is considered zero. So, the constraint that we had is, and by the way, double counting didn't matter. So that if this if this station doesn't get more than 0.5% of its customers being interfered with by either of those stations, then it's not something in our interference law. So that simplified our problem a bit, if we mentioned how complex it would be otherwise. And what happens now is if you make a graph. This is an example from north of New York City. Here's each of the nodes of this graph is the location of a television station. Each edge in the graph is a pair of stations that can't both be assigned to the same channel without creating interference. So this is called co-channel interference, and it's there were more constraints than this, but this was most of the constraints in the auction was, and I'm going to speak as if these were the only constraints, is eliminating co-channel interference. And so nodes that are connected to this one are colored sort of pinkish or salmon, and there are white nodes that are connected to that. And if you take a look at and this was a treaty negotiations with Canada, so we all internationally coordinated in the US and Canada, and we ended up with this map for the connections in the US and Canada. There are about 130,000 edges in this graph of the connections. And a set of stations can all continue to broadcast in a given set of channels if there's a way to assign channels to those stations that doesn't create interference. And if you studied some complexity theory or algorithms and so on, you'll realize that this is a graph coloring problem. It's the same question when you give me a graph and give me a set of colors, channels, colors, the nodes, you assign a color to each node in the graph, assign a channel to each television broadcaster, so that no two connected nodes are the same color, so that no two connected stations in this graph are assigned to the same channel. That's how you eliminate, how you assign them without interference. And about 130,000 constraints, and actually a harder problem than that. But this is a good approximation to the problem. And checking feasibility, if you give me a set of stations and ask me to check, is there a way to keep all those stations on the air with a set of channels that you have available? That's an NP-complete problem, which for those of you who don't know what that means, very roughly speaking, it means that in worst case, the solution times grow exponentially the size of the problem. And you don't want to stick numbers like 130,000 into an exponent. These will be, the worst case problems are just not solvable within any reasonable time that we might want to have for an option. So we won't always be able to tell whether it's possible to assign channels to a given set of stations. So when we proposed during the auction, here's some stations, maybe you should buy these and leave these on the air. We asked the computer, is that possible? The computer will sometimes come back and say, yes, here's the way to do it. Sometimes it'll come back and say no, and it'll say, I proved that to my own satisfaction. There's just no way you're going to be able to check this proof. Or it can say, duh, I don't know, I ran out of time. And all of those things we have to be accounted for in the auctions. So this was hard. And what we did was we generalized something. There have been various descending auctions that have been proposed. We're not the inventors of descending auctions, but we generalized that and created a new class, a full class of descending auctions as follows for buying the television stations that we can use to account for all this complexity that you've just seen. So here's the class, and this is the most technical part of the talk. So the notation is that there's going to be a series of rounds, discrete 1, 2, 3. We know Alex loves discrete, so discrete mathematics, and Vince too. Discrete mathematics, okay. And there's going to be a set of bidders who are still active at time t. So those are those who don't exit at time t becomes the set of bidders who are still active at time t plus 1. The history of the auction in round t is the sets. It's a sequence of sets. Who was active in round 1, round 2, round 3, and so on. Those are the set of histories we can face, and H is the set of possible histories of any length. And a descending clock auction then, with that notation, is a function described by a function, depends how you want to say it. It's a function that maps histories into price vectors. So there's a price vector for each one of the bidders, and it has these properties. No bidder's price ever increases, so the whole vector of prices at time t after any history is less than or equal to the prices at time t minus 1 after the compatible history, the truncated history at t minus 1. Second, inactive bidders, if somebody drops out, we don't do anything to their prices. The prices don't change, so the price at time t to bidder n, if the bidder is not active, is the same as it was at time t minus 1. If a bidder's price is strictly replaced, if I approach Vince over there, and Vince, your grandfather founded a station in God knows where, in Topeka, Kansas, and and I've just offered you $90 million for its broadcast rights, and this round I reduced that price to $85 million for the broadcast rights. You, if you wish, can now exit the auction. If I don't reduce your price, you can't exit the auction. You've already said 90 million was acceptable. But when I drop it to 85, you get another bite of the apple. You can say, no, I wouldn't take 85. And if there's any round in which no bidder's price changes, the auction ends. That means that for any later round, means mathematically that the function doesn't hit as a constant after that point. And the set of possible histories is finite, which is equivalent to saying that the auction has to eventually, which no one really else. But that's the set of auctions. So it's a really big set, which turned out to be quite useful to us. And the bidders who are still active when the auction ends, those are the bidders who sell their stations. We buy their stations from them for these prices. They're the ones we call the winners in the auction. So these are the properties that make this class of auctions so nice. First of all, they're adaptable to accommodate computational. I'm going to show you these properties, but this is the list. They're adaptable to computational limitations. If we sometimes can't calculate what we need to calculate, we can adapt to that. Now we'll show you how. They're obviously strategy proof. In fact, this is where the phrase obviously strategy came from. If you've ever listened to Sheng-Wu Li talk about this, it was quite remarkable. We had these things whose computations we didn't understand, and I thought it was really strange that these auctions were strategy proof when we didn't even know what the outcome functions were. And I said, but it's obvious that they're strategy proof. And Sheng-Wu Li walked away and said, what could that possibly mean? And invented the concept of obvious strategy proof. The weekly group strategy proof, they exist coalitional deviations. They can be extended to accommodate spending constraints, unlike victory auctions, which cannot be extended to accommodate such constraints. They produce something that we'll call competitive prices, and I'll say what that means. And they preserve winner privacy, which is when Vince sells his station to me for $80 million, I never learned that he would have taken $15 million. Okay, the winners preserve. This is for those of you who know something about history. John McMillan had written famously about auctions in Australia, where they ran second price auctions, and there was an auction where some transponder sold at a price of $6. That was the second highest bid, when the highest bid was $1 million, and that didn't play too well in the press. This auction doesn't have that characteristic. Okay, so computational limitations are easy. Given any auction, so take any descending auction and define its adaptive version to be, if I can compute the price, if I can't compute the price, let the price, leave the price constant. If you do that, okay, what do you get? You get something that can always be computed. I can always compute not changing the price. And if the computational failures are rare, then these things don't differ very much. So this becomes something as we improve computations, the rules of the auction are changing in the traditional mechanism design theory. But even though the rules of the auction change, this is still a descending clock auction, which is going to preserve all the other properties that I will show you. Second, these are obviously strategy proof, and here the intuition is simple. Vince is over there, and he's got a station which is worth $15 million to him, and I've just offered $80 million, and he has to decide whether to say yes or no. That's obvious, is what I remember saying. You know, you don't need to know anything else. You don't need to know how to do the rest of the computation. You don't need to know what anybody else is going to do. And it doesn't matter whether other people are reacting to you. You can't do better than to say yes, because if you say no, you keep your station. If you say yes, the worst thing that happens is keep your station. Truthful bidding is what Shendu called the dominant strategy. These things are weekly real strategy proof. That means there's no coalition that has a deviation from truthful bidding that strictly increases all the coalition's members' payoffs. This is really a corollary to obvious dominance. The first coalition member to deviate, well, so there's Vince over there, and I've offered $80 million, and we all have agreed on something. Can he do better by dropping out? Well, he can't do better by dropping out, no matter what we plan to do in the auction. So no. And if it's gone to, if your price is $15 million, if the price is down to 10, can it ever be can you be strictly better off to say yes when the price is 10? Well, that also can't happen. So the first guy to deviate can't benefit. So there's weekly group strategy. Budget constraints. I have a descending clock auction, and I've got, as we did, about $10 billion to spend buying stations. And if the price is $12 billion, well, what I can do, so I've got an auction that if it gets below $10 billion, fine. If it doesn't, if it seems to be stopping at $12 billion, I just keep reducing the prices until it gets below $10 billion. And I may not buy as many stations as I'd like that way, but I can guarantee that I can extend the auction so that it might otherwise would have ended, so that I meet the budget and I preserve all the strategy proofness. The victory auction is the unique way of doing things that also optimizes. So you have to give up some optimization to do this, but you don't lose strategy proofness. For every descending clock auction and every budget, there's a budget respecting the extent that it just means that if you didn't satisfy the budget, when you get to what's going to do in the end, you just keep reducing cycles. It preserves winner privacy. I've already given you the intuition for that. Every descending clock auction with truthful bidding satisfies this winner privacy condition. And if you have a monotonic winner selection rule that's implemented by some protocol that satisfies winner privacy, then it can be implemented by a descending clock auction. These are essentially, this is we like this property that really characterizes what descending clock auctions are. Okay, prices are competitive. I'm going to run out of time if I spend too much time on this, but if you use this method of calculating prices, and if you made everybody fully informed and did the computations for them, they would find that it was a Nash equilibrium in a first price auction for them to bid these prices. And that's what I'm going to mean by competitive prices. You know what everybody else is bidding, you bid the price that's most favorable to you. That's a full information Nash equilibrium. So the prices that emerge from this are full information Nash equilibrium prices. If people were fully informed, this is something that you will do. Okay, I'm going to speed it up a little bit. What do I want to tell you about Meyerson? So the people have, there are auctions like this for the case of substitutes. For the case of substitutes where you actually get efficient outcomes, but in general you don't get efficient outcomes from this auction. But you might be interested in not just efficiency, but in sort of minimizing your expected costs. These are costs the government has to pay. You might have other objectives, And Myerson teaches us that we can minimize expected costs by minimizing the total marginal revenues in the auction, total virtual values, as I should call them. And it turns out you can do that. There is an auction that gives us a greedy approximation of minimizing the virtual costs of the station we buy. It's the same as maximizing the virtual costs of the stations we don't buy. And that very much resembles an abstract problem. No winners skip over it. It's so we can adapt the rule to efficiency or cost minimization. So those as a theory recap, they're adaptable limited computations, obviously strategy proof, group strategy proof. If you take these complex constraints into account, we can accommodate budget constraints and get prices that appear to be competitive, preserve winner privacy. And if we care about something other than efficiency, we can adapt within this big class to find things that do that. What the FCC actually did, I'm going to go quickly through this, is this was the formula we ended up using for the prices. We had a central clock, and we took for each station, we took the number of links it had in the interference graph to the power 0.5. We took the population it served to the power 0.5, multiplied those things together, multiplied it by a round specific constant. This something that so this determined the relative prices of different stations. And if we could prove that it was feasible to get a station on the air, then we reduced its price. We couldn't prove it. It's an NP hard problem after all, an NP complete problem. We couldn't always tell sometimes, but if we couldn't prove that there was a way to put your station on the air, then we committed to buy it and just froze its price at the previous price. And let me see what I want to do to go quickly. Yeah, we ran some simulations to see how this worked, and this will give you some idea of what the performance was like. It's too hard to calculate the actual optimum in this problem. As I already indicated, it's a very hard problem computationally. But if we took just this area in the Northeast United States within a couple of links from New York City, that was a problem that we could just barely compute. Compute the optimum for, so we could compare performance of our auction compared to an optimum performance. We compared to the Victory auction, and this gives you some idea of the improvement that we've got. If you ran the Victory auction using the computers we had at the time, it took 90 CPU days to find the optimum and all the prices. If you ran it our way with our auction, it took 1.5 CPU hours. It's like 3 orders of magnitude difference. And in particular, it was feasible on a national problem. The Victory auction was not feasible at all on the national problem. If you think about the value of the stations that are left on the air, we weren't trying to maximize that because we were interested in cost. We gave a big weight to cost that we were doing. But the stations that were on the air, stations that were taken off the air in the Victory auction, if you normalize their value to 100, the clock auction took off stations with a value index of 105. They took off slightly more valuable stations we didn't optimize, but the costs were much lower, about 25% lower for running the auction the way we did compared to the Victory auction. And we were targeting a mix of cost and efficiency criteria, so people at the FCC liked it. Okay, this is actually, I have only a few minutes, so let me just try to do this one quickly, because this is really the heart of it. To achieve change from the status quo ante, and this is supposed to describe both spectrum and water, the priorities have changed. We need organization, we need leadership. In radio spectrum, Obama had a national broadband plan implemented in an act of Congress that gave us the authorities that we ended up needing. There were unknown externalities from new uses. We had measurement, spectrum study. We're proposing measurement, a hydrological model. The private transactions are ineffective, and they're going to be ineffective in both of these cases because of the massive externalities that are involved, which is coordinated use. There was legal protection of existing uses, and we're proposing to keep that both for radio spectrum and for water, where we had a voluntary auction to get people to transform their rights into a different kind of right. We were told that, we were bound to fail in radio spectrum because there were people who were just totally committed. So, for example, religious broadcasters in Chicago, public television stations in San Francisco. Turns out money speaks. In San Francisco, KQED, those of you who know San Francisco, had 3 broadcast towers and discovered by upgrading its technology, it could serve essentially all of its state population with just 2, and had $95 million to its endowment. It thought that was a good deal. It was a religious broadcaster in Chicago. They got $480 million for Chicago broadcast rights, and discovered they could save a lot of souls with $480 million. And it sold its rights. So, money talks, and overcoming resistance seemed important. But we have no pecuniary externalities. The biggest difference to me is pecuniary externalities. In spectrum, we have technical innovations only. If you take too much water out of a farming area, you change the community. And that's a big deal. And we haven't quite worked out how we want to limit water transfers out of the community as part of the process. But that's going to be important because the farm workers, feed stores, the guys who sell farmers, everybody, the whole communities are built around farming. And I think I'm pretty much out of time. There's some shared characteristics. I guess I'll just close with, there's a lot of shared characteristics. I just have this hope, and maybe this is too big a deal. Maybe I'm biting off more than I can chew here. But we had, when we started this project, we had a huge crisis before the last 2 rainy seasons. In California, we had a 20-year drought going on. And the Colorado River, the big reservoirs in the Colorado River were running dry, nearing what's called dead pool, where the levels of the reservoir were so low that there wouldn't be any more electricity generated by the Hoover Dam and by the, some of the major sources of electricity in the whole Western, or the whole United States, actually. I think Hoover Dam is the largest single electric source in the entire United States. And the federal government was starting to demand action. And we thought this could be a time when there might be legislation and something where people recognize there's a need for change and something big could be done. And if we had a plan ready, we would get a hearing. And then we had the last 2 rainy seasons where we had a temporary agreement by the states to reduce the water use. We had a lot of extra rainfall in the last 2 seasons, which has been helpful. So I think there's a crisis coming, but it isn't right now. And we hope to have a plan ready for when the crisis is here and people say, we need to do something. And we say, here's what you could do. And I'm hopeful that I'll be back in a few years telling you how we changed water rights in the US West. Thank you.
Thank you both for the excellent talk.
Thank you. So it's really cool that computational difficulties played an important part in your exercise. I'm curious about the history. Sometimes things are incomplete and in fact they're actually solvable. What did it take to realize that this one isn't just too big?
Well, so first of all, thank you for asking and reminding me. I should have mentioned Kevin Leighton Brown all along here. There's a computer scientist at UBC who made amazing contributions to how this calculation was done. But the computational difficulties we recognized were important from the beginning, and in fact, they had a deep influence on the whole design, and I didn't say anything about that, but I'll take this opportunity. When we started, we had the idea that maybe what we would do is broadcasters who took on a little interference would sell rights where they accepted that they were going to give up 5% of their broadcast rights. Where we'd start allowing broadcasters to sell some amount of interference. And that we didn't do entirely for computational reasons. The computations drove that. This design, I wasn't sure how hard this was. This is a story for all of you. And Kevin thought he knew how to do this, so he took we had run some experiments, computational experiments, and he took these out-of-the-box algorithms that took how long would it be to check a single station, and to see whether I was going to be able to fit it on. And with the kinds of problems that we thought would come out of a spectrum auction, and the best out-of-the-box algorithms, we ran them for 5 minutes, and none of them solved half of the problems. And I was looking at actual time for real-time auction. We needed to solve 99% of the problem in 1 minute. And here was not half of the problems in 5 minutes. And then Kevin went to work with machine learning on algorithms for, this was the first part of the work that he did. He did a lot of stuff. But the first part of the work, he did machine learning on parameters, of highly parameterized heuristics, and the median runtime went from over 5 minutes down to a seventh of a second. And I thought, okay, he's going to be able to do this. So we are going to get to where we can solve this kind of problem. And it's what determined what we were buying and selling. I mean, the computations were absolutely essential to this formulation. So we knew it was hard from the beginning. And we designed it to be a little easier. That is, the computations that I thought we would be able to do. And it was Kevin's work that isolated this. So Kevin Brown, I should have mentioned him earlier.
Thank you. So you presented your work in the context of also coursework, and use that as part of motivation. But in the context of these common poor resource problems, there's also the work of Lee Ostrom, which is quite different. The work that you presented is very technical, it's in a developed society, and Lee Ostrom has done a lot of work on common poor resource problems, also including water, but in quite different settings. So I'm sure you've thought a lot about this, and I wonder if you could comment a little bit on when each one of these approaches would work and why we want to consider, one of them or the other.
Yeah, thank you for that. That's another great question. So Ostrom's work was mostly about local public resources. So, you could, if we share a lake and the fishermen all know each other and we're fishing and we're worried about overfishing in the lake, we can make up rules. And so the community allocations become very important. And I think that mostly what's gone on in markets in California so far is local markets for very much the same reason. We have a basin that contains the groundwater in a certain area. And there we can hope that the solution doesn't lie in what I'm showing. We can hope that the farmers get together and agree on some other allocation process. So Ostrom's work is very important. And if we can solve the whole problem with local markets, I'm not 100% sure that we can, by the way. I didn't start there. Maybe we can solve it with something simpler. But I think that's where Ostrom's work most applies.
Can you do the last question?
I just had a question. In terms of extracting like this, right here. Extracting like the option format, obviously carbon emissions is a common issue. Instead of using a carbon tax, has there been any look into using this kind of option format where each government sets, say, the arbitrary limit on how much carbon there can be, and then using the option for companies and individuals?
There has been. In fact, I'm talking with Boli in China about, their they have carbon permits and they have permits, not a tax. And they're allocated on some historic basis so far. The question of grandfathering and of how you allocate them. Right now they have, I won't try to go into describe the Chinese system, but I don't think it's a very good one. But they basically give you permits in proportion to your output, which basically subsidizes, output increases, so. Anyway, it's basically an output subsidy the way it's currently allocated. But they're talking about going to some auction format. They're worried about the costs to their producers and having some discussions about that.
Fabulous. Thank you so much, Paul. Thank you again. Thank you.